universe began, light has remained unchanged. Now man has created a new kind of light with powers and properties unlike anything that existed before. Laser light.
That's kind of the beauty of math, though, isn't it? Like it's.
Yeah.
I think what always amazes me about math in particular is how we see it's a completely abstract notion, right? Like if I asked you, show me one, what would you do?
I'd be like this. I got one finger.
Right, but that's one finger.
Yeah.
But it's not one.
It's not
right?
one. Yeah.
So it amazes me to no end that we were able to sort of come up with this body of knowledge. It's completely theoretical. And then in nature, we find like, oh my goodness, this thing exists in nature, or there's a relationship in nature. And the most extreme example I can think of this is string theory. For the longest time, quantum mechanics, the physical realm has been explained by sort of two bodies of knowledge, quantum mechanics and general relativity. General relativity is fantastic for very large bodies. Like if I asked you, like, if Ryan, if you're an astronaut and you're trying to orbit Earth, like, you're just, free orbiting Earth, we can use relativistic mechanics to calculate your orbital trajectory, what physical effects your body might have. And for very small things, like for the transistors in our computers, electrons and super small particles, quantum mechanics does a wonderful job. But there are there's certain physical scenarios where both of them break down. Like none of them they don't really overlap nicely. And physicists have always been upset at that. They don't like that there are certain, physical phenomena that are not cleanly explainable with quantum mechanics or they don't agree in certain areas, like what happens at the edge of black holes, for example. So string theory was kind of an answer. It's a proposed solution to that problem. And a lot of physicists call it, you might hear in the news, they call it the ultimate theory of everything. Have you heard of that term before?
I have.
Theory of everything.
Right.
Because
so it's what connects mechanical and like quantum, the different ways of solving problems in physics.
That's a good surface level interpretation. I think the real nuance here is it's not that we can't get them to play nice. If you do a little more research, or if you take like a first year graduate course in quantum mechanics, you'll learn about relativistic quantum mechanics. So normally in like our undergraduate studies, the electron or the particle is at a really slow speed. It's sort of we don't really care how fast it's going. But in Europe, or when you're a particle physicist, you're flinging this particle at like 99% the speed of light. So you really need to factor in those like the Lorentz transforms and all that stuff.
Right.
So it's not that they don't really play. It's just that there are certain phenomena, things that happen in nature that neither of them seem to agree on, and we want to find a way to make them play nice. So.
Right, because calculations for going at speed of light are different than if you were just in a car, right?
Right. No, precisely. Einstein and Lorentz. I mean, you remember those crazy problems we had to do, and like Bob and Alice is going at like 0.8 the speed of light, and I'm like,
and she has like a clock, and she's going on a train, and Bob's stationary. Find the time dilation between Bob and Anna.
The thing that kills me though is like for physics, like finding the Lorentz transforms wasn't like I hated the Lorentz transforms, but I loved the Schrödinger equation, like solving that second order. That was actually fun, but that's because it's relevant to my work in quantum mechanics or quantum computing. So, but I digress. So going back to string theory, the basic idea is that normally when we do math with particles, we assume the particles are points, right? They're singular. They have almost little to no mass in our assumption. So with string theory, we actually say that all matter can be represented by these kinds of vibrating strings, and the different configurations of those strings, which are super, super tiny. Like it's almost like I think at Planck's length, but these strings vibrate and they loop on themselves, and the way they interact. The math behind this can actually could potentially help, or is promising in explaining those unexplainable phenomena. So that's what it's. But we have yet to find experimental proof, but and there's a lot of argument too, because people are saying like a lot of physicists are investing too much time or too much energy into a theory that could be totally wrong. Like, it could, we have to throw it out the window, because before string theory, there were other, attempts at something like this, but they also sort of fell apart.